Hi everyone. Today I'm going to introduce our recent work, transformer-based multi-aspect, multi-granularity, non-native English speaker pronunciation assessment. My name is Yuan Kong. I'm from MIT. This is a joint work with Ziyi, Yixin, Peng, and Jim. We have our code released at this link. First, I want to introduce some background of this project. Computer assistant pronunciation training, or CHAPTER in short, is an important technology for self-directed language learning, which facilitates non-native or L2 speakers to learn foreign spoken or L1 language. Compared with conventional classes, CHAPTER is more economical and convenient. It also allows language learners to receive immediate feedback on their pronunciation. There's quite many work on this topic, but the motivation of this work is we find pronunciation quality includes many aspects such as fluency, prosody, stress, and multiple granularity such as the phone, word, and utterance level. However, previous methods typically model these aspects and granularities separately. Phone, word, and utterance level scores of accuracy, fluency, prosody, and stress are potentially correlated. Therefore, modeling them together jointly instead of separately has the following advantages. First, it allows a machine learning model to learn a more comprehensive representation and improve its performance. And in reality, it is also desirable to have a single model that can assess multiple aspects of pronunciation simultaneously. With this motivation, we propose goodness of pronunciation transformer, or GOPT in short, which is the first CHAPTER model that measures multi-aspect of pronunciation quality at multiple granularity simultaneously. Here is an overview of the GOPT model. We have tested a few pre-trained acoustic model, which we will introduce in the next slides. And we also use some goodness of pronounced features as the input of the transformer. We will go detail into the features. The input of the system is, of course, the audio and the canonical phone transcription. The reason why we also input canonical phone transcription is that it's important to let the model know which phone is the correct phone. Then we input the projected GOP feature to the transformer encoder and achieve first utterance level representation and the second phone level representation. And we then apply a regression head to these representations to get a set of scores, including utterance scores, word scores, and phone level scores. With these scores, we use a multitask learning framework. Namely, we calculate the utterance level loss, word level loss, and phoneme-level loss. And then we combine these loss as the loss of the entire model. And then we train the model end-to-end. We use SpeechOcean 762 dataset for our experiment. SpeechOcean 762 is a free open source dataset designed for pronunciation assessment, which consists of 5,000 English utterances collected from 250 non-native speakers. So one special thing about SpeechOcean 762 is it provides very rich label information. Specifically, it provides 5 utterance level aspect scores: accuracy, fluency, completeness, prosody, and total score. The 3 word level aspect scores: accuracy, stress, and total score, and 1 accuracy score for each phoneme. Thus, it provides a total of 8 labels for different granularities and pronunciation quality aspects. Each score is annotated by 5 experts. On the left hand, I'm showing the criteria for each score. So let's go to the acoustic model in detail. In this experiment, in our experiment, we evaluate the performance of 3 pre-trained acoustic models. The first acoustic model we evaluated is a public ASM model trained with Librispeech 960 hour data, which is completely L1 data. The model is based on factorized time linear network and trained with Cody recipe. It is available online with this link. We intentionally use a public ASM model as for our main experiment for easy reproduction of our results. Besides this model, we also tested 2 acoustic models that is trained on both L1 and L2 speech, which generally generates better alignment for L2 speech and may output better GOP features. To explore if GOPT works with different acoustic models, we actually compare the acoustic model trained with different settings. So for the acoustic model trained with both L1 and L2 speech, we have PAI1A, which is trained with 452 hours of L1 data and 1,696 hours of L2 data collected from about 6,000 non-native speakers. And the third model is PAIB, which is trained about 1,000 hours of L1 data and about 7,000 hours of L2 data from 672K non-native speakers. We use the GOP feature defined in one previous work for easy reproduction. Specifically, we use the log form posterior and log posterior ratio as GOP feature. These 2 features are defined in these equations. We then concatenate LPP and LPR feature of each phone as a GOP feature vector. In our experiment, we use 42 phones. Therefore, the feature vector is an 84-dimensional feature vector. As I mentioned before, we add 1 regression head to each phoneme, word, and utterance level label. So each regression head is just a dense layer with layer normalization. For utterance level, the regression head add on top of output of the transformer out of the corresponding utterance level token, namely the CLS token. And phoneme and word level regression heads are added on the top of transformer output of each corresponding phoneme. We propagate the word score to each of its phoneme during training and average the output of phonemes that belong to the word in inference. And we use mean square error loss for each assessment task and apply multitask learning. To make the weight of each loss same, we normalize the score before applying the loss function. And the entire network is trained end-to-end. So let's see some experimental results. We compare our GOPT model with an LSTM baseline as well as previous works. It was mentioning that all these methods are based on same acoustic model, which is trained on Librispeech. So it is a fair comparison. We find that GOPT model achieves new state-of-the-art on most assessment tasks, while the does fail on one task, which is the utterance level completeness assessment. We hypothesize the poor performance is potentially due to the highly imbalanced training data on this score. We find that the multitask learning scheme can also be applied to LSTM. However, LSTM's phoneme-level and word-level assessment performance are worse than GOPT, demonstrating that the transformer architecture is better at modeling fine-grained pronunciation units. We also try to use another acoustic model, which is PAIA, that is trained on both L1 and L2 speech data. And we found that it significantly boosts the performance for phoneme and word level assessment, but not utterance level assessment. PAIB lead to similar results, so we skip that in this table. We also conducted a set of ablation studies. We find that GOPT trained with multitask learning achieves better results than any single task learning model, demonstrating that multitask learning not only allows the model to conduct multi-aspect and multi-granularity pronunciation assessment simultaneously, but also improves the performance of each individual task. And we also found cognitive form embedding is crucial to the performance, as the model trained without perform much worse for all tasks. Finally, we find increasing either the width or depth of the network cannot further improve performance, indicating that a small model is preferred with a relatively small data set. So to conclude, we present GOPT, the first transformer-based multi-aspect, multi-granularity pronunciation assessment model. We leverage the recent Speech Ocean 762 dataset with rich annotation to train the GOPT model in a multitask learning scheme. We show that with the multitask learning scheme, a single GOPT model can conduct multiple pronunciation tasks simultaneously, and its performance is better than the same model trained with a single task. It was to highlight that GOPT achieves new state-of-the-art on all phone, word, and utterance level tasks. Finally, we'll also conduct a series of ablation studies to show the performance impact of each design choice of GOPT. I want to remind you that the GOPT code is released online in the link, in this link. Please have a try if you are interested. Thanks.